Welcome to The Explainer. Today, we are talking about something that, and I mean this literally, holds our entire universe together. We're diving deep into chemical bonding. Let's get right into it. So, have you ever just looked around and wondered, what stops everything from, just drifting apart into dust? What holds the water in your glass together? The phone in your hand? The very air you're breathing? Well, the answer is chemical bonds. These incredible, invisible forces build our whole world, one atom at a time.
Now, to really get a handle on bonding, you have to understand the one thing that almost every atom wants. You see, most atoms are actually pretty unstable on their own. They're on this constant, lifelong quest to find stability. And to do that, they look up to some very, very cool role models.
Say hello to the celebrities of the periodic table, the noble gases. These are the guys way over on the right-hand side. And why are they so special? Well, it's because their outermost electron shell is completely, totally full. They are perfectly balanced, perfectly stable. They don't need to react with anybody. And pretty much every other atom out there is trying to be just like them. This deep-seated need for a full outer shell actually has a name. It's called the octet rule. And you can think of this as the #1 rule in chemistry. The main goal, the driving force, is to get a stable set of 8 electrons in that outer shell. And this goal dictates everything an atom does next. So how does an unstable atom get that perfect set of 8? Well, it really boils down to 3 main strategies. They can lose electrons, they can gain electrons, or they can share electrons with other atoms. Lose, gain, or share. That's it. These 3 simple moves are behind every single chemical bond we're about to look at. All right, let's start with the most dramatic approach, a straightforward give and take. This creates what's called an ionic bond, and it's basically a story of one atom giving an electron and another one taking it. So, let's meet our characters. Over here, we've got a sodium atom. See that one lonely electron in its outer shell? If it could just get rid of that one, the shell underneath would be perfectly full. And on the other side, we have chlorine. It's got 7 outer electrons. It's so close. It just needs one more to complete its set of 8. I think you can see where this is going, can't you?
And here it is, the big transfer. Sodium gives its extra electron over to chlorine. And just like that, boom, both atoms win. Sodium now has a full outer shell, and chlorine has a full outer shell. They've both achieved their ultimate goal. They're stable. They have satisfied the octet rule. But there's a really important catch. When the sodium atom lost a negative electron, it wasn't electrically neutral anymore. It became a positive ion. And when chlorine gained that electron, it became a negative ion. So they got the stability they wanted, but they had to become charged particles to do it. Now, we all know what happens when you have a positive and a negative, right? Opposites attract. This powerful force is called electrostatic attraction. The positive sodium ion and the negative chloride ion are now stuck to each other like magnets. And that powerful attraction, that is the ionic bond.
And this attraction doesn't just stop at one pair of atoms. Oh no, it builds up into this huge, perfectly organized, repeating 3D pattern of positive and negative ions. We call this a giant ionic crystal lattice. In fact, the next time you sprinkle table salt, which is just sodium chloride, what you're actually holding are trillions of these perfect little crystal structures.
Okay, but what if giving or taking electrons just doesn't make sense? What if it's easier for atoms to cooperate? That brings us to strategy number 2, covalent bonding. This is all about sharing, and it's the main way that nonmetal atoms team up.
Let's go back to chlorine. Imagine 2 chlorine atoms meet. Each one needs 1 electron. Instead of one stealing from the other, they come up with a clever plan. They each put 1 electron into a shared space right in the middle. Now here's the cool part. Each atom gets to pretend that both of those shared electrons belong to it. It's a perfect win-win, creating what we call a single covalent bond. But why stop at sharing just one pair? Take oxygen, for instance. Each oxygen atom needs 2 electrons to be stable. So they each put 2 electrons into the pot, forming 2 shared pairs between them. This creates a much stronger connection, known as a double bond.
And you guessed it, we can take it even further. Nitrogen, which makes up most of the air around us, needs 3 electrons. So, 2 nitrogen atoms will share a whopping 3 pairs of electrons. This is a triple bond, and it is incredibly strong. It's a simple rule. The more electrons they share, the stronger the bond between them.
You know, scientists have a few different ways of drawing these molecules, kind of depending on what we want to focus on. A dot and cross diagram shows us every single outer electron. A structural formula uses simple lines for bonds. A model can show us the 3D shape, or we can just use a simple molecular formula that tells us what's in it. They all show the same molecule, just in different ways. So we've seen giving and taking, and we've seen sharing between atoms. But what happens when you have a whole bunch of metal atoms all crowded together? Well, they have their own unique strategy. This is metallic bonding, and it's the secret to why metals are so strong and why they conduct electricity so well. Here's how it works. In a chunk of metal, all the atoms agree to give up their outer electrons, but not to any one specific atom. Instead, they donate them to a huge shared collection. The bond is the attraction between the positive metal ions left behind and the surrounding sea of free-floating electrons. Just picture it. You have this fixed grid of positive metal ions, kind of locked in place. And flowing all around them, through them, and between them is this fluid sea of electrons. These electrons don't belong to anybody. They belong to everybody. It's this moving sea of negative charge that holds the whole structure together so tightly, and it's also what allows electricity to flow right through it. Whew, okay. We've done ionic give and take, we've done covalent sharing, and we've done the metallic community pool. Let's just take one step back and put it all together to see the big picture. This chart lays it all out perfectly. Our single goal is chemical bonding to achieve stability. From there, we have our 3 paths. You can go the ionic route, gain and lose electrons to form a giant crystal. You can go covalent, share electrons to make individual molecules. Or you can go metallic, create that sea of electrons to form a giant metal lattice. 3 totally different strategies, all leading to the exact same place, a stable, full outer shell. So there you have it, the fundamental rules that atoms follow to build everything. The water in your body is held together by covalent bonds. The electrical signals firing between your brain cells depend on ions from ionic bonding. You are a masterpiece built from all of these different bonds working together. So the next time you wonder what holds the world together, remember, it's the same thing that's holding you together too. Thanks for joining us on The Explainer.